For this first problem, we have a cart beginning from rest, so we know its initial velocity is 0. We don't have any units, so we'll just call it 0 for now. We know that it starts at a time of 0, and then from the top of a long incline, it rolls downhill with a constant acceleration. And then at time t, the cart has rolled a distance d from its starting point. So we know that we have some displacement, and that's equal to d because that's from its starting point. We know the time is capital T here. And then what it wants us to figure out is how far the cart rolled at a time that's 5 times greater, right? So this is the information we know. Because the acceleration is constant, we know that we can use our kinematic equations. So what we want to do is figure out which one here we want to use. So I have the 3, and I need to have something that can relate all these variables together. So in the first one, I have velocity, the initial velocity, I have acceleration and time, but I don't have anything with displacement. So that one's not going to work. In this third one, I have the 2 velocities, the acceleration and displacement, but again, no time. So I need to use this one here, this middle one. All right. So the middle one was x equals x naught plus vx naught t plus 1/2 a sub x t squared. Okay. So if I subtract this, this is really delta x, and then the initial velocity here is really 0, so that would be 0, and then plus 1/2 a, and then t, my time is really big T here. Oh, well, here, we'll just put this for now. Delta x is d equals 1/2 a, and then this little t is really big T squared. Okay? The thing is, it tells us acceleration is constant. All right, so what I'm doing is I have some constant times t squared, and what that tells me is that d is proportional to t squared. So if I'm multiplying the t by 5, then essentially what's happening is that 5 is going to be squared, and then I need to have my d be 25 times as large. Okay, so the distance, right, that distance d, the distance is 25 times greater. Okay, and another thing to think about, because I know some people want to be like, oh, well, if it's 5, then this is 5, right, because it's a direct relationship. But remember, this is a direct quadratic relationship here, right? So this is like my y is proportional to x squared. So if you had this, it's like saying, all right, well, if I made my t 5, then this point would be 5, 25. Then my d value, or my y value, is 25. All right, for the next part, we have these 2 objects, A and B, and they accelerate from rest. Okay, with the same constant acceleration. So A is constant, which that's very important, because the minute we know A is constant, we know we can use our kinematic equations. And we're accelerating from rest, so we know our initial velocity is 0. And then object A accelerates for 9 times the distance as object B. So we know that we are comparing our displacement, and what else? How much faster is the object? So we know we want to find out information about the velocity. Okay. So again, we go to our equations, and I look at the first one, and I'm like, well, you know what? This has time, but our problem didn't talk about time at all. For the second one, we have displacement, we have initial velocity, but again, we have time, so that's not going to work for us. And then the last one, we have velocities, acceleration, displacement, this is the one we're going to use, okay? So I know that v squared equals v naught squared plus 2a, and then instead of the change x minus x naught here, I'm just going to put delta x, the change in position. So then we know our initial velocity was 0, so we can get rid of that. We know then that v squared equals 2a delta x. But again, this part 2a, that's not changing. That's a constant number, which means that v squared is proportional to x. Okay? But remember, this is our independent variable here, and this is the v squared depends on the x, so it's a lot easier to solve for this if we said v is proportional to root x. Okay, so that's going to be more helpful because if I know x, then I can calculate v. All right, so our delta x here should be delta x, delta x. We know object A went 9 times the distance. So what that means is we have the square root of 9 times that displacement. But the square root of 9 is 3. So in order for this proportion to stay, this has to have a velocity that is 3 times greater. Or you can say A is triple the velocity of B at the end of that period. Okay, so the last one at first glance you're like, oh, that looks pretty easy, and you could probably simplify it to make it easy. But what's happening is we have a college physics department, and they attached motion sensors to a soccer player. And at one instant, what it showed was that the acceleration was 20 meters per second squared, and that the velocity at that instant time was negative 10 meters per second squared. And it wants us to describe his motion. Okay, so it wants us to talk about like how he is moving. Now, this is an instant in time, so what I think is the easiest way to kind of explain what's going on is to kind of take a look at if we have the 3 graphs all at the same spot. So I have a position time, and I have the velocity time, and then we have the acceleration time. So I have these 3 graphs, and I know at some instant of time, which I don't know, but we'll call that this mark right here, I know that velocity is negative 10, so that should be down here really. So we'll call this negative 10. So that's here. I know acceleration is at positive 20. And that's all I know right now. And so I'm like, all right, well, how is this guy moving? Well, if you know that the velocity is negative, you already know that the player is moving. In this case, if positive is towards the goal, velocity of negative, positive means we're moving away from the goal. All right, so moving away from the goal. Okay, and then the next thing is to determine how quickly they are moving away. So what I want you guys to remember here is if we are looking at this 20 meters per second, right? That is that's your acceleration. If that's the case, after, let's say this is 1 second later here, right? Just 1 second later. What that means is 1 second later on your velocity versus time, that I have done 20 meters per second. That's what I increased by on my velocity time graph. So then all of a sudden, I'm up here. But if you look at the motion of this guy, here he is slowing down to a stop, and then he is increasing to 10 meters per second. Now, we really want to know what's happening in that instant, so I don't want to know after 1 second. I want to know pretty much right here what's happening. Well, if he's moving 20 meters per second, then this person is slowing down very quickly. Okay? Because if it was a half a second, just a half a second, that person is slowing down to a stop. Because anytime here, we're right in the middle, that's velocity equals 0, right? So within the next half a second, if they continue having this relationship, they're going to stop. So they're moving away from the goal, and they're slowing down very quickly.